So let's start the second session, second part of the morning session with a plenary lecture given by Professor Malcolm Halcrow from the Leeds University. Professor Halcrow graduated at the University of Cambridge. Then he got his PhD in 1992. The Edinburgh University, and after a postdoc in Toulouse and another one at the Indiana University, he came back to UK as a research fellow of the Royal Society of Chemistry at the University of Cambridge. He published about 300 papers on various and exciting topics in modern inorganic chemistry. He developed a very rich chemistry, especially concerning spin crossover materials, mixed valent radical complexes, with a special emphasis to switching metal complexes via electron transfer and valence tautomerism, inorganic supramolecular chemistry and crystal engineering, copper chemistry. Today he will give a talk with the title Structure Function Relationships in the Light-Induced Spin State Trapping from an Isostructural Series of Solvate Crystals. Professor Halcrow, you have the floor or the screen.
Thank you, Marius, for that very kind introduction. That's okay. You can see it. Okay. You can see this all right, please? Okay, thank you. So yeah, I hope I can live up to that very kind introduction from Marius. And of course, I'm also very grateful to Victor and to Sergey and Matvey and the organizers of this meeting for allowing me to present our work today. So this was my title in the abstract, and I will present this work. But since I have 40 minutes, I'm going to present another system as well, which is a little bit related to this topic as well. So here is a long list of names of people that we've worked with over the years. For this talk, the first system I will talk about was made by Ithar Capel, a PhD student who graduated 2 years ago. The second system, which is the main part of the talk, is a little bit older. The compounds were first studied by Lawrence Kershaw Cook, another PhD student who now works at the University of Liverpool in the UK, and then taken on by Raf Komachevsky, who now works for Coca-Cola. I'll present some photocrystallography that was done at the University of Rennes. We do our magnetic measurements in Leeds with Oscar, and I'll present some photomagnetic measurements that were done by Guillaume Chastenay at the Bordeaux group, and some solid state DFT calculations right at the end that were done for us very kindly by Sergei Vela. So I probably don't have to present this slide. This is why we are here. I think we all know what a spin transition is. We've seen them already this morning in Professor Sato's talk and in Dr. Mandal's talk. So I'll go straight on and say that our attitude towards spin crossover has changed a little bit over the years. We often see spin crossover at molecular magnetism conferences, but I've come to think of it more as a problem of crystal engineering rather than of magnetism. We use magnetic measurements to measure spin crossover very often, but these are usually just simple Curie paramagnets at the end of the day. Their magnetic properties are not so interesting. What is interesting is the structural changes that lead to the changes in the magnetic behavior we observe. Effectively, a high spin and a low spin crystal form are two different phases of a particular crystal. So what we are looking at is a crystallographic phase change, but it's a phase change we can study by magnetic measurements or by UV-Vis spectra or by Mersbauer spectra or by EPR, as well as by X-ray diffraction and by calorimetry. So by studying spin crossover, we can learn a lot about the mechanism of crystal phase changes. And this is more the approach that, towards the topic that we're taking now. So if you want to use a spin crossover material for the kinds of applications that people talk about in nanoscience or in devices or sensors, you need a material with the right kind of spin transition. You need the right kind of temperature. You need the right kind of cooperativity. Usually you'll need thermal hysteresis, although that's not always true. Some applications actually don't, you need to avoid hysteresis, but usually for bistability, this is what people look for. But as we'll see, this is just a selection we've published over the years. The form and the shape of a spin transition varies a lot between different materials, from being highly cooperative to being so uncooperative and gradual and incomplete, basically, that you can't publish things like this very easily. And so it's to understand why this crystal behaves very nicely and this crystal does not, you have to understand the molecules in your crystal and how those molecules interact with each other in the lattice, because both of these factors are important. And they're important basically because the structure of your complex or your ion center changes by a significant amount during the crystal phase change between the high spin and low spin states. The iron nitrogen bond lengths here change by about 10%. And of course, this changes in the inner core of the molecule. It's in the inside. But the outer surface of the molecule also must change to allow this inner structure change to take place. And it's that outer change that can lead to cooperativity in the crystal, because it's the outside of the molecules that are touching each other in the crystal lattice, not usually the inside part of the molecule here. So it's what's happening on the outside around here that is actually important for this. So you can sometimes relate the appearance of a spin transition to the changes that are happening at the metal complex, at the cation itself. So we have 3 examples here. This is quite an old slide. But we have here an example where the structure is changing, but the cation is just breathing in and out, in and out. It's just a breathing motion. There's no other structure change. And this spin transition is very gradual. Here we have a very anisotropic structure change. As well as changing its bond lengths, the molecule is changing its shape. And this leads to a much more cooperative and much more interesting spin transition with a sequence of phase changes and hysteresis and really everything you want. So if you're lucky, the complex within the crystal can explain the switching properties you see. However, if your complex is a salt, if it's a cation, for example, then this will not be the only thing in the crystal. You will have anions in the crystal as well. Perhaps you will have lattice solvent. And these inert parts of the crystal also play a role in its function. Now, a classic example of this was published by Professor Bergi in Switzerland, I don't know, 17 years ago now, where he looked at just 6 alcohol solvates of this simple complex salt. And he found that the 6 solvates showed very different spin state properties. 2 of them just stayed high spin at all temperatures. They did no switching. The methanol solvate is very gradual. The ethanol one has 2 steps. The isopropanol solvate has a more complicated switching up here. So the switching properties you see change a lot depending on the solvent. And I should say that all 6 of these materials have the same basic crystal structure, the same basic lattice. They're not perfectly isostructural, but the packing is the same in each case. So Professor Berge at the time was very pessimistic. His conclusion in this paper was it's impossible to understand why the same crystal lattice gives such different switching properties. It's not possible to control this. We might as well give up and go home. But in fact, since 2004, you can start to grow a little bit more understanding of how these phenomena work. And in fact, if you want to understand things like this, what you really need are isomorphous materials, different compounds with the same crystal lattice, the same crystal packing, so that following the scientific method, you can just change one thing in your crystal and show how changing that one thing affects your properties. So if your materials are isomorphous, the lattice is always the same, then you can just change the molecules. So here they're changing the R groups, basically different aromatic substituents here. Or you can change the solvent, which is what Professor Berge did. Or you can change your counter ion, which is what they've done here. Let me close that actually, which is what they've done here, and always get series of materials with the same crystal structure. And if you're unlucky, your isomorphous crystals all have the same basic spin crossover. So these guys are all very gradual and really not very informative. Their properties are all pretty much the same, and it's difficult to learn very much from those cases. But in these ones, you get much larger changes from changing the solvent or changing the anion or changing the substituent. And here now you can compare your crystal lattice, look for small changes, and understand why those small changes lead to very different spin crossover. So that's the kind of thing that we've been looking for more recently in our work. And I'm going to show 2 recent examples of this that we've published. This first one, I hope I can do quite quickly. This is this compound. We do a lot of work with this kind of tridentate ligand. This is probably most of the chemistry we do. Because you can make many examples of this kind of ligand with different substituents in this position or here or here. And it's a very nice library for studying spin crossover compounds and different kinds of crystal behavior. So I'm not going to talk about all these different solvates you can make with this compound, just a few of them. And we first published this 3 years ago with the acetone solvate of this complex, which does a thermal spin transition like this, quite abrupt, little bit of hysteresis, to about 50% completeness, and then it stops. And you look at the crystal structures, the high spin crystal structure is unexceptional. There's a lot of disorder here at the outside of the molecule, but the basic thing is there's nothing of great interest here. But the low temperature crystal structure, I should say that is the asymmetric unit of that crystal. 24 unique molecules in that asymmetric unit. Some of them are high spin, some of them are low spin, And these ones have a mixed high spin population at this temperature. And you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 high spin, 10 low spin, and 4 which are mixed spin states. That's a 1-to-1 high spin, low spin mixture. That's what we see. And there's nothing else interesting about this. I just put it up for the crystallographers who are out there, because this is one of the largest unit cells that is known for a molecular crystal in terms of the number of molecules that it contains, the number of unique molecules. I think this is the second largest, or it was when we published it. The largest crystal has Z prime is 56. So we have a long way to go before we beat that record, but still, it's a nice little observation. However, this guy isn't isomorphous with anything else, and it doesn't tell us anything else. What is a bit more informative are the nitrile solvates. So this is the acetonitrile solvate of this crystal. And in fact, we can isolate 2 solvates with 1 or with 2 molecules of acetonitrile in the lattice. And they are isomorphous, same space group, same unit cells. But this solvate has an extra equivalent of acetonitrile squeezed into a pocket inside the lattice. And in this solvate, this yellow solvent molecule is gone, but everything else is the same. And in fact, you look, the first equivalent of acetonitrile is lost quite easily. The second equivalent is retained much more strongly. So you can study the 2 solvates quite separately. The N=2 solvate is high spin. It loses a little bit of solvent inside the squid. We make a little bit of this stuff, but it's high during the measurement, but it's high spin. The N=1 solvent with less acetonitrile shows a nice abrupt spin transition here. Now, you can maybe understand this if I go back, just because if we have extra solvent in this lattice, then the crystal packing in this structure is denser. We have more atoms in this unit cell than we have in this unit cell. So probably there's just not enough space inside this crystal lattice to allow the structure changes with spin crossover to take place. This is a denser crystal, so kinetically, it's maybe trapped in its high spin form. That's how we understand that. Now, you crystallize from propionitrile. You also make the same crystal phase, but now we have a step in our spin transition. It's not much of a step for the BF4 salt, but for the perchlorate salt is very clear. And the comparison is very nice if we plot the acetonitrile and the propionitrile materials on the same graph. The temperature does not change for the 2 solvents. The perchlorate has a little lower temperature than the BF4, and that's a trend you often see when you do these comparisons, because perchlorate is a larger anion, so it favors the larger high spin molecules, lowers T half a little. But when we change from acetonitrile, we have 1 step, to propionitrile, we have 2 steps, but at the same average temperature. So as you might expect, the step in the propionitrile solvates comes because for this solvent, we have an intermediate phase, which is a mixture of high spin and low spin crystals. Same space group, but double the unit cell size. And then when we go down to fully low spin, we regain the original crystal phase. This is quite well-known behavior now for different spin crossover crystals. It's not so interesting. But again, the more interesting question is, why do we only see this behavior with the larger propionitrile solvent? And we can understand this, I think, when we look at the solvent in the crystal. The high spin crystal, the solvent is disordered, 50% up, 50% down in its orientation. In the low spin phase, the solvent is now completely ordered in one position. And in the intermediate phase, we have two unique solvent molecules. Now, one of them is ordered, but the other is still disordered. So the existence of the intermediate phase, I think, is actually controlled by the ordering of the propionitrile solvent, not by the spin states of the molecule of the complex. It's the ordering of the solvent, and the propionitrile solvent has this bent shape. It's very much bent here like a boomerang. So it can be oriented up or down, and that gives rise to the disorder. Acetonitrile, MECN, just looks like this. It's linear. You can't have the same up-down disorder for a linear solvent molecule. So we don't have the intermediate crystal phase during the spin crossover. And I think this is the difference. And this is a nice illustration of how the shape of the solvent molecule controls the form of the crystal, of the spin crossover we see. It's not the shape of the complex, because the shape of the complex is the same for both of these solvents. It's the shape of the solvent which controls the behavior we see. So that's the first example. The second example is more complicated, and I'm going to present it as a structure function study for light-induced spin crossover, not for the thermal spin transition. So again, and I think we've seen this before, certainly in Dr. Mondal's talk this morning, maybe in Professor Sato's talk as well, that we can also induce a spin state change at low temperature by irradiation for an iron 2 complex. Usually you would use a green LED or a green laser to do this, which would work very well. Gives you a very nice low spin to high spin state change. And at sufficiently low temperature, the material remains trapped in its metastable excited high spin state. And it's only when you rewarm the material, you reach a temperature at some point where now the lattice has enough thermal energy to be able to overcome the activation barrier for relaxation, and it collapses back to its thermodynamic low spin ground state at this temperature. So, I mean, this is nice. You can think of this, that we can study the same process of the same spin state conversion under thermodynamic and under kinetic conditions by doing this experiment and look at their relationship. And if you look at if you plot a graph of the thermodynamic versus the kinetic spin transition temperatures, this was noticed by the Bordeaux group quite a long time ago now. What you see is you get quite a linear relationship as long as you only compare the same kinds of molecules. So these are molecules with monodentate ligands. These are molecules with bidentate ligands. These are molecules with tridentate ligands like ours. There's a lot of scatter here, but you can still just about see a graph if you look hard enough. And these are three-dimensional inorganic lattices. And basically, as your molecule or your ion center becomes more rigid, then the kinetic relaxation at low temperature becomes more difficult, and T least goes up as your molecule becomes more rigid. That's the basic message from this graph. So these are compounds that we've measured, always with the Bordeaux group, I should say. They have done these measurements for us. This is the correlation line that they originally proposed. I think actually this line looks a little bit better for our data, but you know, the basic principle is there. Apart from this compound, I'm not going to explain this compound. It's an old one. It's this paper here, but and it's a long story, but we'll come back to this kind of thing in a few minutes. So these compounds are ones that we've been studying for a few years now. We've published these 3 papers, and now I am going to talk about most of these solvents now. We've made a couple more of these as well. We have about 12 of these. They show a variety of spin state behaviors. Sometimes they stay high spin. Often they show a moderately gradual spin transition. This one example is the most interesting. We have a nice hysteresis here in this guy. But whatever they are, whatever they do, they're always isostructural. Same space group, same unit cell, same crystal packing. And this is what they look like. I should say that we can interconvert some of these by single crystal to single crystal transformations. So you make the water solvate, for example, by heating the acetone solvate for 2 days in an oven. It loses the acetone and then absorbs water in air. The crystals stay good and you can measure them. And then if you heat the water crystals on a diffractometer, you can remove the water and make the solvent-free crystals with no solvent at all. But the crystal structure is always the same. And you can understand this a little bit by looking at the packing, because there's a region of the crystal lattice which is very disordered. And these are layers within the crystal which contain disordered isopropyl groups, disordered solvents, disordered anions. And if we blow that up, you can see. So you can understand maybe how the solvent molecules can slowly move past these mobile disordered residues within the layers to move up or down the layers to eventually exit the crystal. Now, to understand the different shapes of the spin transitions, you think that this disorder might be important. So if you compare, for example, the acetonitrile solvent in the high spin and the low spin form at the same temperature inside the hysteresis loop, okay, we're losing a little bit of disorder in the solvent, but the disorder in the anions, for example, does not change. And if you look more generally, this is the water solvate now. If we cool it down, looking at the disorder, now we're doing the spin transition. We've lost a little bit of disorder now in the isopropyl group, but the rest of the disorder is still there. And we only lose the rest of the disorder at lower temperatures. So I think the disorder is not directly connected to the spin transition. Now, I said we would look at the photomagnetism. This is data from 6 of the compounds showing that they give good least measurements. And if we do this same graph, plot T least versus T half, again, kinetic versus thermodynamic spin transition, we have a perfect straight line for 5 of the compounds. But the 6th compound goes here. And we didn't understand that at all for a long time. It wasn't even clear what question we should be asking, because if you compare these measurements with our other compounds we published earlier, it's actually this compound, and possibly this one, which are closer to the other compounds from our work, and these ones that look like the outliers. So what question should we ask? Should we ask, why is this one different? Or should we ask, why are these ones different? So to try and understand this, we did some crystal structures. We sent crystals of 3 of these compounds to Rennes in Bordeaux, to Eric Collet's lab, and he very kindly measured them for us. The first one he measured was this one. So this is the low spin and the high spin at 20 Kelvin before and after irradiation. And they look completely normal. There is nothing unusual about these compounds. And even the disorder we see in this anion at 20 Kelvin, this disorder is still kept at 20 Kelvin, as in the 150 low spin structure, for example. So there is nothing unusual there. Next, he measured this one, which is the acetonitrile solvent. For technical reasons, they had to measure at higher temperatures, but the same principle. There is nothing really unusual about these structures, and we got a very low temperature structure of the high spin form, and again, there's no difference. And then he measured this one, and this guy is a lot more complicated, because when you cool it down, it does a phase change, a tripling of the unit cell. And it's still low spin here. These are all low spin molecules, but the unit cell changes, and then you irradiate, and it does another phase change. So there's a phase change occurring during least relaxation, and then you warm it up, and by the time it's done the least relaxation, this is it's reverted back to this phase. So this is what we had in 2017. We weren't going to get any more measurements, so we published this, and we said perhaps this phase change explains why these molecules lie on a different straight line than these other ones. But then after publishing this paper, the Royal Society of Chemistry gave us a grant which paid for more helium so we could do more measurements. So 2 years later, we measured the rest of these compounds. And this compound does not do the phase changes, and neither does this one, and neither does this one. So this material is the only compound out of 6 that does those phase changes. So what is going on? Well, so the next thing we did was we measured the temperatures of these phase changes more accurately. And after in the high spin state, after irradiation, so this is the photo-excited crystal, the phase 3 to phase 1 transition occurs at this temperature. You can see in this part of the diffraction image, for example, there are some diffraction spots have gone between here and here. So this is the phase transition temperature, and it's about 20 Kelvin below the spin state relaxation. So in fact, our assumption was wrong. The phase change does not happen with the least relaxation. It happens at lower temperature. And in fact, the phase change has no relevance to the least relaxation. In English, we would say that this was a red herring, or I think an ulovka is the word in Russian, according to Google Translate. So that explains one thing. Another thing to notice is that this guy, the acetonitrile solvate, this is looking at the least relaxation in the crystal using unit cell measurements. And the unit cell volume actually increases a little between the high spin and the low spin state. We get a negative thermal expansion almost between the high spin and low spin. The low spin has a larger unit cell than the high spin. And this is the opposite to the normal trend, and it's very unusual. And it happens because in the low spin state has a much more canted monoclinic unit cell angle than the high spin state does. And this canted unit cell angle, even though the A, B, and C dimensions are a little larger, the canted unit cell angle reduces the volume of the unit cell a little bit to give us this unusual effect. And in fact, 2 of these 6 solvates that we measured by photocrystallography have this unusual, small but real negative unit cell volume change during least relaxation. Now, so Sergey Vela very kindly did solid state DFT calculations for us on these compounds, plus 2 other compounds from our system where we also have photocrystallography data. So I'll show 2 graphs. These are calculated spin state energies versus experimental spin crossover temperature. And you see for the 4 complexes from this system, we have a good agreement. So the calculations are reproducing the thermal spin crossover well. These 2 compounds do not lie on the line, but these are different molecules with different crystal packing, with different lattice energies. So I think it's not surprising that these 2 don't fit on this spin state energy graph. However, you look at the calculated structures now. So this is the volume of the unit cell and how the unit cell volume changes during spin crossover in the DFT calculated crystals. And now 4 of the crystals, 4 of the compounds give good agreements, but 2 of them don't. This one doesn't, but this is the crystal which exhibits the phase change during the least process. So, and those phase changes weren't calculated by the DFT. So it's not surprising that this one doesn't work. However, this one is also not reproduced. The calculated crystal structure for this compound has a unit cell volume which is too high. It should have a negative unit cell volume change, but that's not calculated by the DFT. Now, it's not the negative volume change that's the problem. This compound also has a negative volume change, but this compound is calculated correctly. It's only this one which is not. So I think this is telling us something. The calculations reproduce the thermodynamic spin state changes for this material properly, but they don't calculate the correct crystal structure. So, and if you look, I should say this is not high spin, low spin structures now. This is experimental and calculated crystal structures of this material. And you can see where the differences are. The differences are in the disordered part of the crystal lattice. So this is the solvent, this is the anion, which is often disordered, and this is the isopropyl group, which is often disordered. And the orientations of these groups are not calculated correctly by this DFT. And if you compare this with 2 of the other compounds, for example, the calculated structures in this part of the lattice are much more accurate, are much closer to experiment. So how do we interpret this? The way I interpret this is that this is telling us something about the least relaxation of these compounds, which is a kinetic effect. So we have a material which is trapped in its metastable high spin state. It wants to relax to its low spin, but it has an activation barrier to overcome. And for the acetonitrile crystal, and this is the one which has the T least, which is too high, then the activation barrier is larger because the structure changes in the disordered part of the lattice are much larger than they are for the other compounds in the series. And but especially the orientation of the linear acetonitrile molecule, which is rotating by about 30 degrees between these two spin states. And this solvent rotation is leading to a much larger structure change and a much greater activation energy. And in fact, this structure change is so large that we can say perhaps that this is the thermodynamic structure of the lattice, but the real crystal cannot access this thermodynamic structure because the change in the solvent molecule is too large and the activation energy is too high. And so it's not possible for the crystal to access this thermodynamic minimum. The crystal almost becomes trapped in a false minimum during its least process. That's how I understand it. Sometimes I get arguments from computational chemists who don't like this explanation, but I'm an inorganic chemist and this is how I understand it for now. So to finish, we have a few conclusions from this study. First is that the well-known linear relationship between the thermodynamic and the kinetic spin crossover exists, but it's a little more general. It's not this simple equation. In fact, different materials will give you different relationships, and the slope of the line here, I think, tells you something about the crystal lattice of your material and how it contributes to the activation energy of the least relaxation process. The second conclusion, is that the phase changes we see for this material have no relationship on the least relaxation. And so as a crystallographer, you have to be a little bit careful. You might see a phase change and a spin crossover, but this does not mean that they occur at the same time. It may be that the phase change and the spin state change occur at different temperatures. So as a crystallographer, you have to look carefully to understand exactly what is happening. And then lastly, why do these materials especially have different T least values? I think it's because of the large structure change of the acetonitrile molecule, which is not reproduced by the DFT calculations. And this gives an additional kinetic barrier for the least relaxation that we do not see in the other crystals. So that is everything that I want to tell you, and thank you for listening.
Thank you very much, Professor Halcrow, for the nice and interesting talk. So I will take one question from Victor.
Yes, thank you, Malcolm. Thank you so much for your fantastic, so interesting, so systematic investigations. During your presentation, you spoke about your last publication in ChemCom this year. And I want to ask you, what about, you gave us very interesting example of spin transition complexes One was with tetrafluoride and another with perchlorate.
Yeah.
And one transition was one step, another two step. It was in the middle of your presentation.
Yes. I'll bring it back. Yeah.
It's very, yes, it's a very impressive example. My question, if you will apply hydrostatic pressure, you reach the first step, or you go directly to diamagnetic state?
If you apply pressure to this, well, we haven't done that. We would have to ask collaborators to do that for us. But if you look at pressure studies that other people have done, that Professor Gütlich did, for example, and also the Bordeaux group, what most often happens is that as you apply pressure, the transition moves to higher temperature, it becomes more gradual, but whether you would lose the step, I don't really know. I'm trying to think.
Okay, thank you for your
Okay,
comment.
sure.
Thank you.
So if there are no other questions, please join me to thank again to Professor Malcolm Halcrow for the very nice and interesting talk. And let's go further to Australia. And the next speaker is Colette Boskovic from the University of Melbourne. She's interested in lanthanide chemistry with a special emphasis to magnetism and luminescence. She is also interested in switching metal complexes via electron transfer, valence tautomeric transitions, cobalt radical complexes. So she developed a very rich chemistry, and today she will talk about valence tautomerism in spin crossover and cobalt-dioxelene complexes.
Great, thank you. Good evening from Melbourne, Australia. Thank you very much. That was a very kind introduction. And thank you to the organisers for also the very kind invitation to present our work from the University of Melbourne in Australia to you guys today. It's a real shame that I couldn't be there. Maybe one day I'll get to come to Russia and visit. That'd be really fantastic. I'm going to tell you today about some of our work looking at cobalt-dioxelene complexes, looking at both valence tautomerism and spin crossover. Okay, so we've already seen some quite a bit of spin crossover today and some really nice work there from Malcolm just before. I'm sure everyone here is familiar with spin crossover. Essentially, in most cases, we're talking about octahedral complexes being switched by a stimulus, so heating, light irradiation, or perhaps pressure between low spin and high spin forms. So Malcolm spoke there about iron 2 complexes. Today, I'll be speaking about cobalt 2 complexes. A little bit more complicated than spin crossover is this phenomenon of valence tautomerism. So in valence tautomeric systems, you have a stimulated intramolecular electron transfer between a redox active ligand and a redox active metal. The stimuli that induce those transitions are the same, so heating and cooling, light irradiation, or pressure. But you have that redistribution between two different charge distributions in your complex. So the family of complexes that are by far the best known to exhibit valence tautomerism are cobalt-dioxelene complexes. So just to quickly go through that. So in those complexes, just focusing on the thermal transition, at low temperature, you have a cobalt-3 form coordinated to a catechol version of the ligand. When you heat it, you get electron transfer from the catechol to the cobalt-3, reducing it down to cobalt-2, and you end up with a radical semiquinonate ligand. Now, a really important thing accompanies that electron transfer, and that is that you see a spin transition from low spin cobalt-3 to high spin cobalt-2. So here we have the relevant potential energy wells and also the electronic distribution. So of course, as we go from low spin cobalt-3 to high spin cobalt-2, we're populating formally sigma antibonding Eg orbitals. So as a consequence, all of our metal donor atom bond lengths all increase by about 0.2 angstrom. So the whole molecule increases accompanying that thermal transition. So those longer bond lengths mean a higher density of vibrational states. And this thermal transition, like spin crossover, is driven entropically with both vibrational and electronic contributions. So just a really simple system. This is actually the first system we looked at. And this is my very first PhD student, Jan Miliana. So really simple mononuclear complex, cobalt coordinated to 2 trans-pyridyl ligands, 2 3,5-ditertbutyl dioxylenes, low temperature. This is cobalt-3. One of those dioxylenes is in the catechol form, the other one's in the semiquinone form. We can heat that system up, monitor it by magnetic susceptibility or other techniques as well. And you can see a really nice transition, half temperature of about 250 Kelvin. So the electrons transferred from the catechol to the cobalt-3, you end up with cobalt-2 and 2 semiquinone ligands. And you can also, at low temperature, at least partially induce that transition by light, as Professor Sato talked about before. So analogous to the least phenomenon in spin crossover. So another really nice family of complexes from the literature published from the Florence group of Andrea Day and Lorenzo Soraci and their collaborators back in 2008. This family of complexes here, we have a cobalt and now 1 3,5-ditertbutyl dioxylene and a tetradentate nitrogen donor and ancillary ligand. So these ancillary ligands are based on tripicolyl amine. You can functionalize them by sequentially putting methyl groups in the 6th position very easily. So you can actually access a family of 4 ligands. So the one with no methyls, 1 methyl, 2 methyl, and 3 methyl. So in this family of complexes, the Florence team found that varying that ancillary ligand very much controlled the charge distribution in the complex and whether or not you saw valence tautomerism. So in the looking at the susceptibility over here, when we have just the plain TPA or the monomethyl TPA ligand, the profile is essentially diamagnetic and we're stuck in the low spin cobalt-3 catechol form across all temperatures. On the other hand, when you have 3 methyls on that TPA ancillary ligand, the chi-T profile is consistent with the molecule being in the high spin cobalt-2 semiquinone form, again, across all temperatures. So it's only when you hit the sweet spot, as we might say in English, we have 2 methyls on that TPA ligand that above room temperature or so, you start to see an uptick in your chi-T, consistent with the onset, at least, of this VT, this valence tautomeric interconversion. So essentially what's happening here really is steric control by the ancillary ligand of the cobalt-3, cobalt-2 redox potential. So a way of thinking about that is as you're putting these methyl groups here, you're increasing that bulk around the cobalt coordination environment. And the best way for the molecule to accommodate that is being in the cobalt-2 form with those longer bond lengths. Okay, so one other literature complex I want to talk about is actually related. So a cobalt complex, again, 1,3,5-ditertbutyl dioxylene, and now a pyridinophane azomacrocyclic ligand. It's a 12-membered azomacrocycle. This is from Hans-Jörg Krüger's group in Kaiserslautern, published and communicated initially in 2010. So they demonstrated, again, really interesting control of the switching again by the ancillary ligand. So they reported 2 analogues in this initial communication. So an analogue where you have a methyl substituent on the amine groups of the ligand and another analogue where you have a tertbutyl substituent. In the case of the methyl, the molecule exists in the cobalt-3 catechol charge distribution at all temperatures with no spin crossover or valence tautomerism. On the other hand, when you have tertbutyl groups on that azomacrocycle, now the molecule exists in the cobalt-2 semiquinone charge distribution, but they do see a transition above about 200 Kelvin, and that in fact is a spin crossover transition going from low spin cobalt-2 to high spin cobalt-2. And this is the only complex, the only cobalt-dioxelene complex in the literature that does a spin crossover transition rather than a valence tautomeric or VT transition. So we thought that was interesting, and another PhD student of mine came along, Tina Tevskarevska here, working with postdoc Elodie Risset. And I thought it'd be nice to just obviously see what happens between methyl and tertbutyl. You know, where do we think we might be there? So I had Tina make the ethyl and the isopropyl analogues of that azomacrocycle, which actually hadn't been reported previously and were turned out to be harder than we thought. So she did a really nice job making those ligands. So you can see here, there's the analog with the ethyl substituent. Here's the analog with the isopropyl. We made those cobalt complexes with a 3,5-diterbutyl-dioxelene. Now, crystallography is really useful for us in VT chemistry because those of cobalt-dioxelene systems, at least, because those bond lengths are really indicative of the oxidation state and the spin state. So at 100 Kelvin, in both of these complexes, the bond lengths are entirely consistent with low spin cobalt-3. That's the cobalt, oxygen, and nitrogen bond distances, and also the bond distances of the dioxelene ligand, again, very indicative of the redox state of that ligand. So in both cases here, they're in the catechol oxidation state. So when we went to look at magnetic susceptibility measurements, first of all, these black triangles here are the ethyl analog, and essentially that's diamagnetic at all temperatures up to 400 Kelvin. So that's in the low spin cobalt-3, catechol, charge distribution, temperature invariant. On the other hand, the blue squares here are the isopropyl analog, and that's in the solid state. They're the blue squares. And you can see above room temp, it's essentially diamagnetic at low temperature, and then above room temperature, there starts to be an uptick. So in fact, it looks like in that isopropyl analog, we're starting to see a spin, some kind of interconversion. And from those chi-T values, that looks to us like a valence tautomeric interconversion, not a spin crossover interconversion. And again, when we look at that in solution, so we've got 3 different solvents here, acetonitrile, dichloroethane, dibromoethane, we can actually see chi-T values and chi-T profiles consistent with almost a full VT interconversion, depending on the solvent. So going to the high spin cobalt-2 semiquinone form. So that struck me as being absolutely fascinating, just varying those R groups on the ancillary ligand that you wouldn't really think would have very much to do with VT or spin crossover transitions. You can not only control the charge distribution, but you can control which type of transition that you get. So we started collaborating with a really fantastic collaborator from the Southern Federal University there in Russia, Alyona Starikova, and she has done some invaluable DFT calculations on these systems for us. So just to show you, she calculated all the analogs with the different R groups from the methyl, ethyl, isopropyl, tert-butyl. In the case of the methyl analog, the low spin cobalt-3 catechol is the lowest energy state, and the cobalt-2 semiquinone forms are quite high in energy, and they're too far away for us to see any sort of transition. On the other hand, when we move to the ethyl, so again, just putting ethyl substituents here in these positions on the amine, you can see that the steric effect of that really is again starting to stabilize the cobalt-2 forms, which are both low spin and high spin, are coming down in energy. So again, we still, those forms, that especially that high spin cobalt-2 semiquinone, is too far away for us to access the VT transition at an accessible temperature. On the other hand, when you go to the isopropyl, the calculations actually show that the low spin cobalt-2 semiquinone electromeric form there is actually at the lowest energy, although the low spin cobalt-3 catechol is very close. Experimentally, we find the low spin cobalt-3 catechol form, but now the high spin cobalt-2 semiquinone has come down sufficiently in energy that we can actually access that VT transition, and we see that experimentally. But then when you go all the way to the tert-butyl group, now the low spin cobalt-2 semiquinone form has been stabilized so much that that really is that ground state. And then the high spin cobalt-2 semiquinone has come down enough in energy that you can actually access that spin crossover transition that Hans-Jörg Küger and his co-workers saw. So a couple of things here. First of all, these DFT calculations are really powerful, and really nicely consistent with our experimental data. And again, emphasizing that point that very small changes to those ancillary non-redox active ligands are really influencing the charge distribution and whether you actually see a VT or a spin crossover transition. Just to finish off, nice little bit of work looking at the electrochemistry. Obviously, these systems are really redox active, so electrochemistry is really powerful for us too. So this is Tina and another PhD student, Gemma Gransbury, working together. So with Tina's complexes, the ethyl complex, the isopropyl complex, cyclic voltammetry and acetonitrile, room temperature, both of those complexes are in the cobalt-3 catechol form. There's a lot of redox processes happening here, so we don't need to worry about those. What we are concerned with are what we call the frontier processes. So the first oxidation and the first reduction. This is using the convention that positive potentials go to the right. So the first oxidation is the oxidation of the catechol to the semiquinone, quite nicely reversible. And the first reduction is the reduction of the cobalt-3 down to the cobalt-2. So you can see as we go from the isopropyl to the ethyl, the difference in those processes is about 100 millivolts. And we've started calling that parameter delta ox minus red. We've looked at lots of our complexes and literature complexes. We've come to the conclusion it's obviously condition variable, but in this sort of conditions in acetonitrile, a delta ox minus red of about 750 millivolts, that separation between the first metal process and the first ligand process is what we need to access a VT transition at reasonable sorts of temperatures. So once those processes become further and further apart, obviously that's a proxy for the energies of the orbitals. They're becoming further apart and you're not able to access that transition. So that's a really handy rule of thumb for us to use in the lab when we make a new complex to see whether we think it'll do a VT transition or not. So just moving on to the second part of the talk. So I've always, or for quite a long time, been interested in polynuclear complexes, and I wanted to look at dinuclear complexes to see if we could access a two-step VT transition analogous to what's been seen for spin crossover. And the idea there is you can potentially make a three-state molecular switch. So in other words, a molecular traffic light. So with traffic lights, obviously you can interconvert between the three states. You can sit at any one of those states and you can readily distinguish between the states. And of course, that's been achieved with dinuclear iron 2 spin crossover complexes for a long time. There's many examples of those known. And there's some really nice fine tuning that goes on with those complexes. So for instance, a family of iron 2 complexes with a bipyrimidal bridging ligand. In those complexes, you can vary the terminal ligands. So in this case, it's isothiocyanate. And by varying the terminal ligands, you can actually control whether you get a sequential spin crossover at the two iron centers or a step or a simultaneous spin crossover. So you can go, depending on where you are, in the isothiocyanate case, you have a two-step transition where the two irons transition sequentially, and in other analogues, you have a one-step transition where they both go at the same time. So that's been well understood, I think, for quite a while in terms of the energetics that's required to achieve that two-step transition. Essentially, to get a two-step transition, you need the mixed spin state to be lower in energy than the halfway point between the low spin and the high spin form. So that's been well known for quite a while. I think what's been a bit less clear is what actually causes that low spin, high spin, mixed spin state to be lower, less than halfway in energy. And some nice work from Jordi Suera and Eliseo with computational work have shown that that very much depends on the electronic structure of the iron 2 ions and arising very much just from the local coordination geometry of each of those iron 2 ions. So for my money, that's something that perhaps is not necessarily very easy to control. So you can do it with spin crossover. We were keen to see if you could do it with VT just to see if you could. I mean, you might say, well, why would you want to? And there's quite a few reasons, I think. One is if you're talking about color-based or chromic applications, you can access different colors. That's a simple one. The other thing I think that is more important is that with valence tautomerism, you've got intrinsic redox activity and electron transfer. So I think it perhaps lends itself better to types of multifunctionality that make use of that electronic transfer. So perhaps switchable catalysis or something like that. And I do wonder if it might prove to be ultimately to be easier to control than spin crossover in some ways, based on that idea that's come from Eliseo with his calculations. Okay, so we set out to do this quite a while ago now. So obviously we were thinking, how do we do this? We want a dinuclear cobalt complex that'll do this two-step VT transition. So we set up our cobalt dinuclear complexes. We use that nice family of TPA ancillary ligands that we can tune very nicely to control the VT switching at each cobalt center. We wanted to have dioxylenes there. So the key was really how we actually linked those two dioxylene units together. So the possible profiles, if the molecule does do a VT transition as we want, or what we wanted, of course, was something like this, a nice two-step transition. Other possibilities, of course, are a concerted one-step transition where both cobalt-dioxelene units transition at the same temperature. And of course, you can also access various types of partial or incomplete transitions, essentially corresponding to switching only at one of those cobalt-dioxelene units. So I'll tell you now that the answer really is to do with the intramolecular electronic communication between the two cobalt-dioxelene halves of the dinuclear complex. So if you think about it, it does make sense. I mean, if there's no communication, if these two halves of the dimer can't feel each other, then they're both going to go at the same temperature. In that case, what you'll see is a concerted one-step transition. On the other hand, if you have full conjugation or delocalization, then essentially you're in a situation where you're only going to get something like a partial or incomplete transition. So for the two-step transition, you want some electronic communication, but not too much. And that's the key, as I'll hopefully show you as we go through. So this is work from PhD students Kerwin Alley and Gemma Gransbury. We've been looking at this really nice Spiro conjugated bis-dioxelene ligand that I'll just call Spiro. It comes in two forms, or in our hands it comes in two forms. So it's got the version where the X's here are protons, or the version where the X's are bromo groups. So Kerwin worked on the original Spiro complexes where they're protons, and Gemma then followed up with the bromo complexes. And we made various analogs using those different versions of the TPA ancillary ligands. And here you can just see a crystal structure of one of the bromo analogs. You can see a beautiful sort of hinged dinuclear complex with that spirocyclic carbon there, really acting as that hinge point between the two halves of the dimer. So I'll just take you through some of the results there. First of all, on the left here, we have the Spiro complex. This is the susceptibility data. So in that version where we have the plain TPA ancillary ligand, just like in that monomer from the Florence group, that's temperature invariant diamagnetic. So that dimer is actually stuck in the low spin cobalt-3 catechol on both halves of the dimer form. And again, crystallography at 100 Kelvin, the bond lengths are entirely consistent with that. On the other hand, when we go to the trimethyl TPA, so again, like the monomer, both the crystallography at 100 Kelvin and the variable temperature magnetic susceptibility is telling us that that dimer is pretty much stuck in the high spin cobalt-2 semiquinone form at both halves of the dimer. So the sweet spot in this case, again, is the dimethyl TPA. So it's with the dimethyl TPA that we actually see two steps in our Chi-T profile, and that's the closest thing that we have to a two-step VT transition. This one is, we can go up and down and cycle back and forth over that transition, and the higher temperature step is associated with solvent loss. So that one tends to change as we heat it up too far. But essentially what we believe is happening in this complex is that the first transition corresponds to switching at one half of the dimer, and then the second step corresponds to switching at the second half of the dimer. But when we go to the bromo Spiro, things are a little bit different. So now the plain TPA analog, again, is as before, stuck in the low spin cobalt-3 catechol form at all temperatures. Things that are different though, the dimethyl TPA now is essentially diamagnetic up until about room temperature, and then there's just a bit of an uptick there. So in this case, with the bromo Spiro, now the dimethyl TPA complex, we're just starting to see that first transition at one half of the dimer. And the crystallography at 100 Kelvin is, the bond lengths are consistent with that. So we'll call that an incomplete VT transition. And really quite interesting is the trimethyl TPA case. So now both the magnetic susceptibility and the crystallography at 100 Kelvin are consistent with us at that temperature being in the mixed valent state. Okay, and then again, we did variable temperature crystallography as we heated that up, and our magnetic susceptibility measurements consistent with just seeing that second step, if you like, of the VT transition. So that's what we call a partial VT transition. So again, Aliona's DFT calculations really came into play here and really beautifully helped us to understand what was going on in this system. So she calculated the different analogs with the bromo Spiro. So here we have the plain TPA case. You can see the cobalt-3 catechol at both halves of the dimer is clearly the lowest in energy, and the other form, the other electromeric form, is very high up in energy, and we're basically just stuck in the cobalt-3 catechol at both halves, which corresponds to the red data points in the susceptibility there. When we go to the dimethyl TPA, so now we're putting methyls around that TPA, we're starting to stabilize the cobalt-2 containing forms. They're coming down in energy. And we can see now that that mixed valent state is actually low enough in energy that we can just start to see that onset of that first step of the VT complex. So that's the data points there in blue. Then when we go to the trimethyl TPA, so now the cobalt-2 containing forms have actually come down so far in energy that the mixed spin state is actually the lowest in energy. And then the cobalt-2 semiquinone at both halves of the dimer is again quite close in energy and certainly an accessible energy. So in that case, we actually see what we call that partial VT transition, or where we're seeing the second half of the dimer transitioning as if the first half already had. So that's beautifully in agreement with our experimental data. And then Aliona went back and she calculated our original two-step complex, which was with the plain Spiro ligand, the dimethyl TPA, to have a look at the energies. They're exactly what they should be for a two-step transition according to what we know from spin crossover. So the cobalt-3 catechol at both halves is at the lowest energy. Then you have the mixed valence state, and then you have the fully cobalt-2 semiquinone, all at accessible energies, and the mixed valence state is less than halfway between the energies of the two homovalent or homospin states. So exactly what you'd expect from what we know from spin crossover to see a two-step VT transition. So again, just finishing off with a bit of electrochemistry. So obviously this idea of intramolecular electronic communication between the two dioxelene units is really important. If we have a look at our paper, you can have a look. We've looked at near infrared spectroscopy. We've looked at variable temperature EPR spectroscopy, but there's some nice insights just from the electrochemistry. So in the electrochemistry in these spiral and bromospiral complexes, we always see a beautiful pair of often reversible processes that correspond to the spiral ligand. So in these two red complexes here, the complex is in the cobalt-3 catechol cobalt-3 form at room temperature in acetonitrile. So in that case, those processes correspond to sequential 1 electron oxidation of the spiro ligand, whereas if we're in the trimethyl TPA of the bromospiro, that's in the cobalt-2 semiquinone cobalt-2 form. So those two processes there correspond to sequential 1 electron reductions. In any case, the potential separation between those two processes correlates with the electronic communication across that bis-dioxelene ligand. So whether it's a spiro bis-dioxelene or any bis-dioxelene. So we've started calling that parameter delta diox. I've already introduced this delta ox minus red, which is the separation between the first metal-based process and the first ligand-based process. So Gemma then was able to essentially develop, using that electrochemical data, a sort of a phase diagram or a correlation diagram. We've got delta ox red, so that's the difference between the first metal and the first ligand-based redox processes, versus delta diox, and delta diox is the separation between the two dioxelene processes. So that's the measure of the degree of electronic communication. So if delta ox and delta ox minus red are too large, either positive or negative, we're stuck in either one homovalent form or the other, so the cobalt-2 semiquinone or the cobalt-3 catechol. So that's not what we want. So it's only when the delta ox minus red is at a smaller value, those processes are close together, and that's when delta diox comes into play. So if delta diox is too small, the communication is too small, we just see the concerted one-step transition. If delta diox, if the communication is too great, instead we see the partial or the incomplete transitions. So it's only in this sort of intermediate spot where we can see that two-step transition. We can actually map the values of all of our complexes there. So for instance, the plain TPAs that are stuck in the cobalt-3 catechol form, the ones that do the VT transition, the bromospiro, the communication just seems to be a little bit too much that we don't see a two-step transition that we want. So it's only in the case of the plain spiro that delta diox is just a little bit less that we seem to be sitting in that two-step regime. And we can also plot on this diagram some literature complexes from other people. So for instance, this one here, we've got a sort of a thioether linkage between the two dioxelene units. And in that case, they only see a concerted one-step transition, and that correlates with insufficient electronic communication between the two dioxelenes in their bis-dioxelene ligand. So just to summarize a few things, the DFT is proving to be a really powerful tool and really a nice agreement with the experimental data. Two-step VT seems to require the relative energies of the different electromers basically along the lines of two-step spin crossover. So the mixed spin or mixed valence state has to be less than halfway in between the two extreme forms. In order to get a two-step VT transition, therefore, that requires small but non-zero electronic communication between the two halves of the dinuclear complex. And if you like electrochemistry, which not all of my students do, we've got a nice little correlation diagram that will apply for any of these bis-dioxelene complexes so we can sort of figure out where we are in terms of getting two-step VT if that's what we want to do. So just to finish off, to thank the people that did the work, my students, Gemma, Tina, Elodie was a postdoc, Kerl and Gowan were students, and our crystallographer, Robert Gable. Really nice calculations coming from Eliana Starikova. Other collaborators, Lorenzo Soaci and Giordano Panetti in Florence, Keith and his team at Monash, Carolina Sanudo in Barcelona, and Colorado State, Matt Shores and his student, Brooke Livesey. Australian Research Council funds my research, and we do have time on the synchrotron for crystallography sometimes. And I also just wanted to advertise, if anyone is interested to come and do a PhD in our group, We're nice people. We do interesting chemistry. Melbourne's a nice city to live in. So scholarships are available to start next year when the Australian borders, we believe, will reopen to international people, either in switchable 3D complexes, as I've talked about, or also in rare earth or lanthanide chemistry. Due date there is 30th of September, so just send me an email if you're interested in that. And with that, I will thank you again for the opportunity and for your attention.
Thank you, Colette. We are a bit behind the schedule, so I will take only one question. So if there are not questions.
Yes, there is one question.
Okay.
Thank you. Hi, I really enjoyed the talk. Thank you. So a short question. So you put two cobalt or two cobalt ions into one complex in order to achieve a two-step transition, and you showed that you can do this. You can achieve this two-step transition in some cases in the solid state. And I wonder if it is possible to get a two-step transition in solution.
Yes, it is. I actually have some extra slides that I didn't get. So
okay.
Yeah, with that dimethyl TPA spiral, it does do the transition this is in butyronitrile. It goes yellow to blue-green. As isospecific points, it's quite beautiful. If we plot from that data the fraction of high spin cobalt-2 semiquinone versus the temperature, it's sort of a distorted sigmoidal profile. And if we actually take the first derivative of that, we do see two distinct peaks.
Wow.
So we think, all right, it's not super duper conclusive, but we do think that we in fact are seeing two-step VT transition in that solution. And if it is the case that it is solution, then that's makes it very clear that it's of intramolecular origin. It's not to do with crystal packing or any of those types of effects. So we think so. I mean, we could perhaps have, and I mean, the DFT is consistent that could be. So I think that's reasonable.
So if this effect is true, would it be the very first two-step transition in solution?
That's what we said in our JAX paper.
Okay.
Yeah. We'd like to make another one.
Nice.
I mean, I can't speak for spin crossover, but certainly for VT, yes.
Great. Thank you.
Thank you.
Thank you very much, Colette. And now we go further to the last speaker of the first session. She's coming from the Gunma University in Japan, Motoko Asano. She's a young scientist interested in EPR, polymeric materials, luminescence, and paramagnetic organic molecules. So, Motoko, you have the screen.
Thank you, Chairman. Thank you for kind introduction. And I would like to also thanks to organizer to invited me for this occasion. Can you hear me? Good.
Yes.
So my talk is concerning an open shell compound, but not about the molecular magnet. And also, actually, my talk is concerning triplet energy transfer, but the system has Unpaired electron, and in that cases we can acceleration of the energy transfer rate, and I would like to talk about the mechanism for this acceleration. So the energy transfer is a very crucial and fundamental process in nature and artificial systems. And as you know, for example, photosynthetic reaction, energy transfer, I'm sorry, photon energy was collected to the reaction center by energy transfer, and also in a transition metal complex and lanthanide complex, energy transfer migration is very crucial to determine the optical property in the crystals. However, we sometimes met acceleration. I'm sorry. Acceleration of the. I'm very sorry. We sometimes met acceleration of the energy transfer rate when we have an observer spin, additional spin in the system which is not involved either donor or acceptor. A little bit in a separated distance, this spin makes some rule in acceleration. So please let me remind you about the mechanism for energy transfer in normal cases. If the energy transfer occurs in a close distance, as you know, the two famous mechanism is known. One is Firster and the other is the Dixon mechanism. In the case of Firster mechanism, main interaction is the dipole-dipole interaction, and this causes the singlet-singlet energy transfer. On the other hand, in the Dexter mechanism, exchange interaction governs the energy transfer rate, and in this case, singlet-singlet and triplet-triplet both energy transfer can occur. When the system has a longer donor and acceptor distance, energy transfer is governed mainly by dipole-dipole interaction or super exchange interaction. In that case, the two electrons doesn't have cross overlaps, so there is no direct exchange interaction. So Dexter mechanism doesn't work. So my question is, in the presence of unpaired electron, how acceleration of energy transfer occurs? This is just comparison between the diamagnetic systems and paramagnetic system. Porphyrin is a very well-known compound which coordinates many metal ions. Zinc porphyrin and free base porphyrin dimers undergo triplet-triplet energy transfer very slowly. It's usually the millisecond order. Of course, it depends on the distance between the two donor and acceptor. In contrast, in kappa porphyrin, which has unpaired electron in the ground state, and kappa porphyrin and free base porphyrin dimer undergo intermolecular energy transfer very rapidly. So with the presence of additional unpaired electrons, shared triplet-triplet energy transfer is greatly accelerated. So the aim of this talk is why the triplet-triplet energy transfer is accelerated in the system involving unpaired electron, and how is the dependence of the linkage between the donor and acceptor. So the role of the unpaired electron, and I would like to also clarify
Dr. Asano, we do not hear you anymore.
Seems some connection problem.
Can I continue now?
Yes, of course. Yes. Now it's okay, yes.
Okay.
We can hear you and we can see you.
I start. So the okay. So the free base polyphene has a little bit lower excited state than the corresponding kappa polyphene. Actually, the lower column shows the absorption spectra of the dimers, and the kappa polyphene, the free base polyphene dimer shows absorption spectra which are almost coincident with the superposition of the monomers. So we can say that excited state, electronic state structure of the excited state is not so perturbed very much. So before talking about dimers, just let me explain us briefly about kappa polyphene, because the symbol of which represents excited state kappa polyphene is a little bit not normal. Kappa polyphene in that kappa has D9 configuration. That is, kappa has one unpaired electron in the orbital, and the polyphene has a pi electron compounds, and if the excited state of excited triplet state, the pi electron interact with kappa d electron, and the whole system is no more than the triplet state, and as you know, it should be quartet and a doublet. But the nature of the excited state is very close to the polyphene triplet state, so we call that the doublet state of the triplet origin is triplet doublet, and the quartet state of the that has triplet origin we call triplet quartet state. And also polyphene singlet state became single doublet state. Then in this background, interstation crossing from the singlet to triplet, exactly speaking, single doublet state, triplet doublet state is quite fast. It is less than picosecond, and the fluorescence from the single doublet state is not observed, and we can observe phosphorescence from the equilibrium state of triplet doublet and triplet quartet state. So here is a detailed energy diagram kappa polyphene, the free base polyphene dimers. If we excite kappa polyphene, before that, I have to explain how to describe the excited state. Actually, we should describe the both state and the total spin state of the whole system. So now I kappa polyphene and free base polyphene sequential, and here we see mainly kappa polyphene. And if excited kappa polyphene from the excited singlet state, this means the single doublet state to the undergo the intersystem crossing, and we yield a triplet doublet and a triplet quartet state. In that case, free base polyphene is a ground state, and then energy transfer occurs from the kappa polyphene excited state of the free base polyphene. Actually, if excited free base polyphene, just we can yield excited singlet state of the free base, but the whole system is a doublet state because the kappa polyphene is a doublet state. Then the dimer undergoes intersystem crossing and produces the triplet state of the free base. Here, kappa polyphene is in the ground state, and the free base polyphene the triplet state, and the total spin state is a mixture of the doublet and quartet. And both processes cause the same excited state, where free base porphyrin is a triplet and kappa porphyrin is ground state, and the doublet spin and the triplet spin of the free base is weakly coupled. Then actually we investigate energy transfer from the kappa porphyrin to the free base porphyrin. However, direct singlet energy transfer from the kappa porphyrin to free base is ruled out by the excitation spectra of the fluorescence of free base porphyrin. So this is the result of tangent absorption spectra in which we excite the kappa porphyrin dominantly. If we use 592 nanometer, we have observed transient absorption spectra in which the free base triplet is generated from the kappa porphyrin triplet. The red one shows the first prompt spectra, which is almost constant of kappa porphyrin, and then we can see the blue spectra, which constant of the triplet spectra of the free base, and the rate of the generation of the triplet state depend on the linker space of molecules. So from here, we can determine the energy transfer rate, and if the linkage is a phenylen, we have approximately 200 picosecond, and naphthalene and phenylen, we have almost 400 picosecond. And this number is not correlated to the center to distance of the dimer, and seems to be correlated to number of the bond which connect to porphyrins. So just let me explain what we have observed by the transient absorption. If in the case of a diamagnetic zinc porphyrin free base porphyrin dimer, energy transfer from the zinc porphyrin triplet to the free base triplet is very, very slow, and the energy transfer rate is approximately millisecond or longer. However, if we have one unpaired electron in the donor, energy transfer rate is quite accelerated. It is observed less than nanosecond, and this rate depends on the spacer units. So on the other hand, we excited our free base part selectively. We can observe intersystem crossing within the free base. So this here we see the time dependence of the transient absorption spectra. This expresses the transient absorption change from the singlet state absorption to singlet absorption to the triplet absorption of the free base part. From here, we can also calculate intersystem crossing rate of the three dimers, and this rate is 400 picoseconds, approximately 900 picosecond, and 1000 picosecond. And actually, intersystem crossing rate can be also determined by the fluorescence spectroscopy, and these values are very good. These values shows very good correspondence, and we can believe that this expresses the intersystem crossing rate of the three dimers within the free base. Actually, free base monomer shows intersystem. Free base monomer only shows has intersystem crossing about 12 nanoseconds, so that in the dimer, intersystem crossing is much accelerated, and this order is similar. Phenylen, naphthalene, phenanthroline as similar in the energy transfer from the kappa to free base. So this table is summarize the energy transfer rate from the kappa porphyrin, the free base porphyrin, and enhance the intersystem crossing rate within the free base porphyrin in the dimer, and also number of bonds and center to center distance. Now we see that if we consider center to relation, energy transfer rate and enhanced intersystem rate versus center to center distance, we see no correlation. However, if we take number of bonds that represent the pathway between the two porphyrins, it shows a very good correlation. So we thought that the enhancement energy transfer and intersystem crossing is governed some three bond super exchange like interaction, but we have to notice that there is a small difference between the enhanced intersystem crossing energy transfer rate. So why in intersystem crossing and energy transfer rate so the slight difference dependence? This gives us a hint to consider the mechanism. So now we think about the mechanism of the enhancement energy transfer from the kappa porphyrin to the free base porphyrin. And we have observed also the energy transfer and intersystem crossing has a similar but slightly different spatial dependence. And we are almost sure that this concerned with the kappa porphyrin unpaired electron. So to think about the mechanism of the energy transfer, we define the initial state and final state. We have two candidates for the initial state. Initial state, one is triplet-doublet state of the kappa porphyrin, and the other is triplet-quartet state of the kappa porphyrin. And the final state is only the one free base triplet state. But in this system, we have to think about both kappa porphyrin and the free base porphyrin. So here is a matrix element for energy transfer and wave functions. The initial state, as I said, triplet-doublet state of the kappa porphyrin. But this triplet-doublet state is mixed with a partially single doublet state of the kappa porphyrin. This is because exchange interaction between kappa unpaired electron and porphyrin by electron. And in the case of the B, kappa porphyrin triplet state, kappa porphyrin triplet-quartet state, this is rather pure triplet-quartet state. And the final state is porphyrin free base triplet state. And in the case of the free base triplet state, which is partially mixed with porphyrin free base singlet state via the kappa porphyrin unpaired electron. So to calculate matrix element of the matrix element of the initial and final state, operator is inverse of the this distance. So as you know, two electron interaction, we have, if expand this term, we have two terms. One is Coulomb interaction and the other is exchange interaction. The part one, pseudo-Coulomb interaction is replaced by dipole-dipole interaction. This causes a Felsen mechanism. And the second term is electron exchange interaction, and this causes a Dixon mechanism, and this allows singlet and triplet energy transfer. So actually, if we have doublet precursor, direct matrix element of the triplet doublet state and free base triplet state, matrix element, this is just exchange interaction, which is unfortunately this is the same matrix element when with the zinc porphyrin, and this causes no enhancement. However, the triplet doublet state can be mixed to single doublet state, and this triplet state can mix as excited singlet state, and this excited singlet and the singlet state has a matrix element which causes a Felsen mechanism. So the enhancement is considered to be occurred triplet doublet state and the triplet state of the free base porphyrin through this Felsen term due to the interaction of the upper excited state. On the other hand, in the corrected state, we found that there is no enhancement. We have a matrix element which is exactly the same with the zinc porphyrin cases. Actually, this is a little bit complicated, so I would like to show some summarized figure. So we have acceleration of we have observed acceleration of the energy transfer. In this case, there is a two candidate of the precursor. In the triple corrected state, the matrix element there has no acceleration component, but if triple doublet state, this state can mix upper excited state, and this final state can mix upper excited state, and through this process indirectly we can observe much enhancement of the energy transfer. Actually, these figures will explain the difference of the energy transfer and enhanced system crossing, because enhanced this intersystem crossing just controlled by the through bond surface exchange interaction, but energy transfer cases we have dipole-dipole interaction, which is controlled by the only distance, but also controlled super exchange interaction. So the acceleration of the energy transfer due to additional spin is governed of combination of the dipole-dipole interaction and the super exchange interaction. So this is a conclusion, and I would like to acknowledge my collaborators. Ken Kobori has graduated last spring, and other people, and thank you for your attention. Thank you very much.
Thank you very much, Dr. Asano. I think this is a very interesting lecture and point of view for our community. And I think we can take one question. If the
Boris, you can follow up with live mask.
yes,
Yes.
Professor Triplet, yes.
Thank you for your very interesting talk. I want to ask you to comment one point.
Yes.
In actually, Forster and Dexter rules include not only matrix element of transfer, but also phonons, because phonons ensure
I'm sorry.
change in the energy when transfer occurs. And this is explicitly expressed in the factor that is overlap of the luminescence band of donor and excitation band of acceptor. And this reflects the role of vibrations, and they are very important while comparing the different mechanisms of energy transfer versus length of the band and so on. And this factor also should be present in the discussion. Would you like to comment this point?
Do you suggest vibrational mode concerns the energy transfer?
Sorry?
Sorry, I couldn't hear just in the middle of your comment. And would you like to say that both how the vibration mode of the molecule can concern the energy transfer mechanism, energy transfer rate, because of the overlap of the electron density can change? Is it right?
Yes, thank you.
Okay,
Thank you.
so actually, in that case, Dexter mechanism doesn't work because Dexter mechanism, as you know, needs direct spin over electron overlaps, and now in that case, dipole-dipole interaction, we don't have vibration may change the angles between the two dipoles, and but the most important is the superexchange interaction. It is indirect interaction, indirect exchange interaction, and so the exchange interaction just neighborhood to neighborhood. It depends on how it works. So rather geometry should works sensitively works, but in that case vibrational
Thank you.
That is so much. This is my opinion.
Thank you very much.
Thank you.
Thank you again. And please join me to thank all the speakers for their nice and interesting contributions. And we stop here, and at 1 p.m. we'll start the second session. So thank you very much.
Thank you very much.